Hello and welcome. In this video, we will be looking at how good our approximations are for finding the sum of an alternating series, looking at alternating series error. So I look forward to working through this with you, and let's jump right in. So let's first look at this series, which is the alternating harmonic series, which we already know converges. And let's think about partial sum. So let's first think about what would be the sum if we just looked at the first term, meaning if we just plugged in 1, and that would give us -1. Well, what if we looked at the first two terms? That would give us -1 plus the second term. The second term would be 1/2. So that would be an approximation of -1/2. If we looked at the first three terms, that would be -1 plus 1/2 minus the next term, which would be 1/3, and that would be an approximation of -0.83. Repeating, if I looked at the first four terms, -1 plus 1/2 minus 1/3 plus 1/4, that's going to give me an approximation of -0.583. Repeating. So I want you to think about, we could obviously keep going to come up with a better approximation. The more terms we have, the better the approximation is going to be. So if we think about this, the very first approximation that we made using only the first term is the worst approximation of all the approximations that we made. -1 is too small, because what we're doing to this sum is then adding the next term. So -1 is the worst possible approximation. Well, the next worst approximation would be if we only used two terms. So S sub 2 is a better approximation than S sub 1. However, it's still not great, but I want you to see what we're doing. We're taking this approximation, which is too small, and we're adding something smaller to that. And then we're going to subtract something smaller, and we're going to add something smaller and subtract and add. We're going back and forth, adding and subtracting different values. So S2 is a better approximation than S1, but what we did here was we added too much. So by adding 1/2, we've now overestimated. -1/2 is too big of an approximation. Similarly, if we look at the approximation of the first three terms, we now subtracted our last term, so we've now gone down too much. So if you think about this, I'm going to try and give you a visual here. If we start with just S sub 1, which we know is -1, we said that that is too small. If we take S sub 1 and we add the second term, now we're at -1/2, and we said that this is too big. The actual sum has to be somewhere in between those two values. Now, every time we add another term, like S sub 3, we're now moving back this way. We're getting closer to the right sum, but we're going too low. If we add the fourth term, now I'm over here at S sub 4. Again, I'm getting closer and closer and closer to the actual sum. So again, the more terms we have, the closer we are to the actual sum. The problem is that we couldn't find the actual sum. If we could find the actual sum, then we wouldn't need to talk about how good of an approximation we have. We would just say this is the sum. We're trying to figure out in this section how good of an approximation there is, or to be able to say our approximation of the sum is accurate to this many decimal places, which would be really important for being able to draw conclusions in a real world context. Being able to say this number is accurate within 1/1000th or 1/10,000th, 1/10,000th of the actual value. So again, we can't find the exact sum, so we want to be able to say our sum is this good. That's the idea here. So every time we added something, our approximation became too large, and every time we subtracted something, our approximation became too small. But we can say with certainty that our actual sum is in between any two values. So what I could say is that the actual sum, which we identified as S, The actual sum is definitely somewhere in between, and I guess I don't need or equal to signs because we know it's somewhere in between these two values. But if I found two new values, if I used s sub 2 and s sub 3, I could say, well, it's actually somewhere between negative 0.83 repeating and negative 1/2. But I could actually keep going, and the more terms that I use, 0.83 repeating, the closer we can get to the actual sum. So that's our goal in this lesson, is to be able to say how good of an approximation we can get using alternating series. The whole focus is going to be about alternating series. We'll talk about error for series that are not alternating when we get into Unit 8. So let's look at some more examples. So what we just said was that each time we add or subtract, each time we add a new term into our series, we get closer to the actual sum. What that means is we can say with certainty what our remainder or our error is. So we can't say that the error is exactly some number, but we can say the error is less than or equal to some particular value. If we could say the error was a number, that would mean we could find the exact sum, which we can't do, which is why we're having this whole discussion to begin with. So the alternating series error-bound theorem, also referred to as the remainder theorem, says when we have an alternating series that converges, so it has to be an alternating series that converges, and we are approximating the sum using the first n terms, we can say that the error will be less than or equal to the absolute value of the next term, or the absolute value of the first unused term. So if you think back to the example that we just did, we just were looking at the harmonic series, negative 1 to the n over n, and we said that the sum of the first 5 terms, the sum of the first 4 terms was negative 0.583. If we wanted to say how good of an approximation this was, we could use the alternating series error-bound theorem to say that this answer is off from the actual sum by, at most, the next term, which in this case would be a sub 5. So we could say that the remainder, or the absolute value of the remainder, or the absolute value of the error, because again, we only care about how far off we are from the right answer. We don't care if we're above or below. We could say the absolute value of our error is less than or equal to the absolute value of the very next term. And if we found the very next term, we would just plug in 5, so this would be 1/5. And if we thought about that as a decimal, that's going to be 0.2. So we could say that this is less than or equal to 0.2. That's not a great approximation, but what we're saying here is that this sum is wrong by at most 0.2, which means we could say that the actual sum is trapped somewhere between negative 0.583 minus 0.2 and negative 0.583 plus 0.2. Oops, I put that decimal in the wrong spot. Sorry about that. We could say the actual value of the sum is trapped somewhere in between these two values. So that's how this theorem works. What it says is that in order to determine the error, all you have to do is determine the next term that you're not using when you're calculating the sum. So here's what you're going to do when you're working through these types of problems. The very first thing you're going to do is make sure that the series converges by the alternating series test, unless the directions tell you that it converges. Then you don't have to do that. Then you need to determine how accurate or how good you want your approximation to be. Typically, this is going to be given to you in the problem. And lastly, you're going to analyze the terms until you find a term smaller than the term that you need for that error. So we just found that the error that we were talking about was 0.2. If I needed my error to be less than this, I would need to keep going and find more terms until I found a term that was less than the desired value. So let's apply this to some problems so you can get to see what this looks like in context. Okay, here we are given a series. It says approximate the sum of the series below using the first 6 terms. So the very first thing we need to do is just go ahead and find the first 6 terms. So pause the video, find the first 6 terms, and add them together. Use your calculator for that. So if I was using the first 6 terms to approximate the sum of the series, I would get that the sum is 0.63194. And notice I'm saying the sum of the first 6 terms, so I don't need an approximately symbol here. If I was saying the overall sum, I would need an approximately symbol. So approximately equal sign, because I'm saying the sum of the first 6 terms. Then it says, now find the upper bound for the remainder of the approximation that we just looked at. So the upper bound, meaning I want to know how good of an error this is. What that means that I need is I want to know what the remainder is, or I want to know what the absolute value of the error is. There's lots of different ways you can correctly write this. This is going to be less than or equal to the absolute value of the very next term. Well, this was the first term, the second term, the third, the fourth, the fifth, the sixth. So I need to look at the 7th term, which, if I just plug in 7, is going to be 1 over 7 factorial. Again, I don't care about the positive or the negative sign here. What that means is that the remainder, and if I plug this into a calculator, is going to be 0.000198. So this approximation that I found here is off by the actual sum by at most this teeny tiny little number. It's that good of an approximation. So it's off, and I'm going to write that in a way you can see it. The actual sum minus the sum of the first 6 is off by at most 0.000198. That's a pretty darn good approximation. It's accurate to at least 3 decimal places. Then it says, find the upper and lower bounds of the actual sum. So if I wanted to say the actual sum was somewhere between 2 values, that's what it's asking us to do here. Well, I'm going to use the answer that we found for S sub 6. The actual sum is going to be more than S sub 6, but less than S sub 7. Well, we already know that S sub 6 is 0.63194. And we just calculated what the 7th term was. So this is going to be 0.63194, the sum of the first 6, plus the new one, 0.000198. So I can say that the actual sum is somewhere between 0.63194 and 0.6321429. So we're trapping the real sum between 2 values so that we can say we know it's somewhere in between these 2 values, even though we don't know exactly what that sum is. Let's look at another example. All right, example 2 says, approximate the sum with an error that is less than 0.001. So what I'm going to say, I'm going to call this sum, I'm going to call this S. So I can say that S is approximately, and I'm going to just start finding terms. If I plug in 0, my first term is going to be 1. If I plug in 1, I'm going to have 1/2. Go ahead and pause the video and just maybe list out 4, 5, or 6 terms, and then unpause the video and see how you did. The next term should be 1 over 4 factorial minus 1 over 6 factorial plus 1 over 7 factorial. And I'm going to see if this is enough terms to get this error. So what does that mean? That means I'm looking for, so I want the first term, that the term itself is less than 0.001. So let's go ahead and look at this. I know this is 0.5. That's not very helpful. 1 over 4 factorial is 0.0416, and you could use a calculator to get this. 1 over 6 factorial is 0.00138 repeating. 1 over 7 factorial is 0.000198. So this is the very first number that is smaller than the error that we want. What that means is that if we want to approximate the error, if we want to approximate the sum with the error less than this amount, we need to use the first four terms. Because the fifth term is smaller than the error. So this is the error, or this is less than the error we need. So I can say that S is approximately 1 minus 2 factorial plus 1 over 4 factorial minus 1 over 6 factorial. And just for the sake of time, I'm actually not going to simplify this to be a decimal. Minus 1 over 6 factorial. And I can say that the error, or the remainder of this sum, is less than or equal to 1 over 7 factorial, which is less than 0.001, which is what we wanted. And this is true by the alternating series error-bound theorem. So we can say that the sum S minus S sub 4, since we used 4 terms, the absolute value of that is less than 0.001. And that was what we were trying to find. So here is my approximation, and it's accurate within 1/1000th of the actual sum. Let's look at some more practice. So if you're feeling confident, I'm going to encourage you to pause the video and work through numbers 1 and 2 here on your own, and then unpause the video and see how you did. Okay, for number 1 here, we're given this series, and it says first to show that the series converges. So let's go ahead and do that using the alternating series test. We can say that the limit as n approaches infinity of 3 over 2n times n plus 1, that limit is 0. We can also say that 3 over 2 to the n plus 1 times n plus 1 plus 1, or n plus 2, is going to be less than or equal to 3 over 2 to the n times n plus 1 for n greater than or equal to 1. Therefore, the series from n equals 1 to infinity of 3 times negative 1 to the n plus 1 over 2 to the n times n plus 1 converges by AST. The next thing it's asking us to do is to find S sub 6. So go ahead and use a calculator to find that. S sub 6 is going to equal 0.5651785. And you can actually put that series, changing this to be a 6. You can do that on your graphing calculator, or you can just find each of the first 6 terms and add them together. Either way, you're going to get this as your sum. And then the last part of this question says, show that S sub 6 differs from S by less than 0.003. So I can say that S minus S sub 6, the absolute value of that, is less than or equal to the 7th term, A sub 7. Well, if I plug 7 in here, I'm going to get 3 over 2 to the 7th times 7 plus 1, so times 8. And if I plug that into my calculator, I can get that this is 0.0029, which is obviously less than 0.003 by alternating series error bound. So I have now shown that the difference between the actual sum and the sum I approximated is less than 3/1000ths of an error. It's off by less than that amount. Okay, if you haven't had a chance to pause the video and try and work through number 2 on your own, I encourage you to do that now. Number 2 is simply asking me to approximate the sum of the series with an error less than 0.01. So the first thing I'm going to do is just start listing out terms and looking at my sum. So I'm going to say S equals this. I'm going to say that S is approximately, the first term is going to be negative 0.8 plus 0.8 over 8 minus 0.8 over 27 plus 0.8 over 64 minus 0.8 over 125. And I'm looking for an error that's less than 1/100th. So I'm kind of looking for a denominator that's less than, or that's more than 100. So I'm going to check this on a calculator to make sure that this is the error that I need, but it appears that it is. If I check this on a calculator, this is equal to 0.0064. So this is the error that I need. That means I'm going to approximate the sum with the first 4 terms. So the sum of the first 4 terms, if I actually combine those, is going to give me negative 0.717. And what I can say is, by the alternating series error bound, the actual sum minus the sum I just approximated is off by, and this says less than, so I'm going to get rid of this or equal to, the next term, which would be a sub 5, which is 0.0064, which is less than 0.001, which is less than 0.01, which is the error that they were asking me to use. So here's my approximation, and here's my verification that it meets the requirement that they asked us to use. What we're going to do now is we're going to focus on some more examples where we're determining how many terms we need to use to get our error within a particular value. Then we're going to look at a couple more examples that are just going to tie some more things together, and then we're going to wrap up. All right, here we go. The directions first say to show that each series converges. I'm only going to do this on the very first problem, and then I'm just going to paste in that proof on all the other ones. But why don't you go ahead and pause the video and show that each of these 4 series converges using the alternating series test. So I'm saying that the limit as n approaches infinity of 1 over n to the 6th is 0, and that 1 over n plus 1 to the 6th is less than or equal to 1 over n to the 6th for n greater than or equal to 1. Therefore, I'm going to call this S. S converges by AST. Why don't you go ahead and do that same first step on the other 3 problems. So go ahead and pause the video again and check that you did in fact confirm that each of these series converges by AST. But really that's the review from the first video before this one about using the alternating series test. Now it says determine the number of terms, so our goal is to find the number of terms necessary to estimate the sum with an error that is less than 0.0005. So what we're going to do to start out is just start looking at terms of this series. So I can say that S is approximately, I'm going to find the first term, which is 1 minus 1 over 2 to the 6th plus 1 over 3 to the 6th minus 1 over 4 to the 6th. I'm trying to figure out how many terms I need, or which term is the first term that gets me less than this value. So I'm going to go ahead and grab a calculator and figure out what these values are. Well, 2 to the 6th is 0.0156. 1 over 2 to the 6th. 1 over 3 to the 6th is 0.0013. That's not quite small enough. 1 over 4 to the 6th is 0.000244. And that will do what I need it to do, 0.000264, because that's less than this error that I need. So how many terms do we need? We need the first 3 terms. So we need 3 terms needed for the absolute value of the error to be less than or equal to 0.0005. And here's why we're actually going to show, since, and I'm going to squeeze this in here, the absolute value of the error is less than or equal to the absolute value of the 4th term, which is 0.000264, which is less than 0.0005. Sorry, I cut into that problem there. By the alternating series error bound test. All right, we're going to follow the same process for number 4. So go ahead and find the first few terms and see if you can figure out how many terms we need. Then unpause the video and see how you did. And I'm going to go ahead and erase the alternating series test proof so that I have more room to write in each of these boxes. So here are the first few terms of this series. The first term that's going to be smaller than the error that we need is going to be this one. So I can say that we need 1, 2, 3, 4, 5 terms, since the absolute value of the error will be less than or equal to the sixth term, which is if I wrote that as a decimal, 0.00043, which is less than 0.0005 by the alternating series error-bound test. Now, number 5, if you start just looking at the behavior of the terms, you're probably going to notice pretty quickly our first term is 1 minus 1 over the square root of 2 plus 1 over the square root of 3 minus 1 over the square root of 4. It seems like it's going to take a really long time. We just got 4 terms and we're only at 0.5. And if we have to get less than or equal to 0.0005, it's going to take a really long time to go about doing it in this way. What you can do is you can think about, I want to know when is this going to be less than or equal to 0.0005, and you can just set this up and solve. So I can take the reciprocal of both sides, which is going to give me the square root of n is less than or equal to 1 over 0.0005. And then I can square both sides, which is going to give me that n needs to be less than or equal to, oh my goodness, 4 million. I'm really glad I didn't try and get to each of those terms by hand. That would have taken a very long time. What this means is the 4 millionth term will give me an error that is exactly 0.0005. So we can say that we need 4 million terms since the absolute value of the error is less than or equal to a sub 4 million, which is less than or equal to, in this case, it actually is exactly 0.0005. If this didn't have an or equal to sign, we would need 4,000,001 terms to guarantee that the error was less than that amount. The approach that we took here, where we kind of looked at what makes the general term less than or equal to that value, could work on any problem. It's really up to you to decide which approach you prefer. Okay, why don't you pause the video and look at number 6 on your own and see how many terms you can get and formalize your answer in sort of this notation here, or this sort of sentence, and then unpause the video and see how you did. So hopefully you had time to work through that. The first 4 terms will give you an approximation of the sum of this series that is no more than 0.0005 off from the actual sum. So we would need 4 terms for the error to be less than or equal to 0.00005, since the 5th term is 0.00026, which is less than 0.0005 by the alternating series error bound. All right, we're going to look at 2 last examples. They're quick ones, and then we're going to wrap up. Okay, here we go. I encourage you to read through these 2 problems on your own, and if you feel like you can answer them without help, to go ahead and try and do that. Pause the video and do that. Otherwise, follow along with me. Number 7, is the 50th partial sum, S sub 50, of the alternating series below an overestimate or an underestimate? Well, the answer to this question really ties back to the idea of, is the 50th term positive or negative? So let's look at the first term. The first term is going to be what I get when I plug in 1, which is going to be 1, which means the second term is what I get when I plug in 2, which is going to be negative 1/2. If you think back to the intro that we looked at the partial sums of the alternating harmonic series, we said that the first term was too small. In this case, the first term is too big because it's positive. The first term is an overestimate. Every term after that is going to be smaller, and I'm going to be adding and subtracting those smaller values. So what this is telling us is that all of our even terms are going to be negative. So if I'm looking at the sum of the first 50 terms, well, that would be the sum of the first 49 terms plus the 50th term. And we just said that the 50th term is going to be a negative number, which means we're subtracting too much away. Therefore, the sum of the first 50 terms will be an underestimate since a sub 50 is negative. We're subtracting away too much, so the sum of the first 50 terms would be an underestimate. Number 8, what is the value of the error bound r sub 4, so the remainder of the first 4 terms, for the alternating series below? Well, the remainder of the first 4 terms would be what we get when we look at the 5th term. And if we plug in 5, we're going to get 4, again ignoring the alternating piece since we're taking the absolute value, over 3 to the 5th. 4 over 3 to the 5th is going to be 0.0164. So what we can say is that the remainder is less than or equal to 0.0164. The sum that we could approximate with the first 4 terms is off by no more than 0.0164. So let's recap what we covered in this section. Alternating series, because we're adding and then subtracting and then adding and then subtracting, if an alternating series converges, in order to identify what the error is, or what the error is less than or equal to, we can simply look at the first unused term, and that's the alternating series error bound theorem that allows us to do that. If we need to find out how many terms we need to approximate a sum to a particular value, we can look at the first few terms and find the very first term where that individual term is less than or equal to the error that we need in a given situation, and we can use all of the terms before that to approximate the sum. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.